let's say you have a time series yt and you have a time series xt, and maybe you have a time series zt. And previously we have made some autoregressive models where we use their own lags to explain their this time series process, and we have used the lags of other models to explain a time series process of yt. But what if you would like to explain all these time series in conjunction? Okay, so then you could use a vector autoregressive framework, and this is just an extension of the autoregressive model, which we are quite familiar with, and the autoregressive distributed lag model. In this case, we have 3 different time series, but in the general case, we have k time series regressions. So we have k number of time series, and these k time series are explained by lagged values for all the k time series. So in our example here, we have 2 time series, yt and x of t, and these are explained by their own lags here and the lags of the other time series. So this is and this is equal for all the included time series in the model, and the only question then, after you've decided which time series should be in the model, then you have to look at what kind of time lag should you include in the model. But we're getting back to that, because what you see is that these variables, they can be regarded as a vector of time series variables. And remember that a vector is a collection of, for example, numbers or vectors in either a column or in a row. Okay, and in this case, we are considering the column vector of time series variables, and in our case, we have the time series variable x and y of t and x of t. So this is a 2-row by 1 column vector. The question now is, how do you estimate these equations? And the slopes of these equations, or the coefficients of these equations, can be estimated by OLS. And you know how to do that in, for example, Stata. And the assumptions for the VARs, the VAR equations, they are the time series assumptions which we presented in the last lecture. That was lecture 9. And if these assumptions hold, then the OLS estimators of the VAR coefficients, the betas and the gammas, this is gamma and this is beta. So these are the coefficients, and if the time series assumptions hold, then the OLS estimators, the coefficients that we get, they are consistent and jointly normal in large samples, which means that we can test hypotheses by looking at the t statistics and F statistics. Just to underscore the similarity of the hypothesis testing in a VAR model and an autoregressive model is that if the time series assumptions hold, then we can apply the usual methods of testing our null hypothesis. So, for example, if we have a lot of data, then the 95% confidence interval can be constructed as the estimated coefficient, either the beta or the gamma, plus minus 1.96 times the standard error. So here we assume normality because we have a lot of data. But one of the main benefits of the VAR framework is that we can test these coefficients across equations. So in the autoregressive distributed lag model, we could only test the coefficients which we use to explain the for example, y variable, but we could not test any coefficients explaining the y variable and coefficients testing coefficients on the x variable. So, or explaining the x variable. But in the VAR structure, we can actually test, for example, the lag order, and if in our VAR 2 model we have the number or lag p lags, then we could test the joint hypothesis that all these lags are equal to 0. And the beta 1 is the coefficient on the lagged value of y explaining the y variable. So this is the number 1 variable. And this beta 2p is the p lag of y explaining the x variable, which is the second variable in our VAR framework. And this gamma 1 is the lag px value, which explains the y variable, and the gamma 2p is the lag px value explaining the x variable. So this combined null hypothesis, or this null hypothesis, contains coefficients from both equations, and this test can be then carried out by using the f-stat, and it's quite difficult to express this here, but it's quite easy to do in, for example, Stata. Already some of you recognize this test because we used exactly this test to get the lag length of a autoregressive distributed lag model. Then we only used, for example, the last coefficient or the last lag of the y variable equal to 0, and the last lag of the x variable equal to 0. But here we can use this f-stat to determine the lag length. But also in the VAR framework, this method can return more lags than is optimal. And just in the case of a single autoregressive equation, we could use the Bayesian information criteria or the Akaike information criteria. And as in the case of a singular autoregressive equation, we choose the specification which has the smallest Bayesian information criteria or Akaike information criteria. And in this case, in the var case, the the Bayesian information criteria is calculated as the logarithm of the determinant, because this is a matrix, and a matrix is just seen as a collection of vectors. So you can just add them or put them side by side like such, and then you get like a large vector with numbers, or well, in this case, numbers in a grid like this. So this is a matrix, and in our case, the matrix is the k by k covariance matrix of the estimated regression errors. And the determinant is a function which works on a matrix. And this determinant returns one number, and you take the logarithm of that number. So in our example, we would have a 2 by 2 covariance matrix, which means that we have 2 rows and 2 columns. And the penalty term here is the number of variables or time series in the var framework times 1 plus the number of variables times the number of lags. So if you add variables or lags to the model, this term actually gets large very quick. One of the major problems with vector autoregressive models is deciding which time series of variables should be included in the model. Because if you include too many variables, then you increase the estimation error if those variables are not related to the other, if the included variable is not relevant for explaining the other variables. So, and in this var framework, then the number of parameters or coefficients which is to be estimated grows quadratically. And you see that if you take k by p plus 1 is the number of coefficients in each of the regressions, and you have k regressions, which means that you have k squared plus k, or k squared p plus k number of parameters in the var model. So if you increase k by 1, which is that you include one extra variable, then you increase the number of coefficients quadratically. So for example, this if we have a var model with 5 variables, this is k, and 4 legs, this is p, then we have a total of 105 coefficients, because we have 5 plus or times 5 times 4 plus 1 coefficients.